All right, guys, let's talk about mass and weight. And this is a pretty critical topic when we start, when we're talking about forces and stuff. So mass is the amount of stuff you have. Amount of stuff. So this is what makes you you. This is the amount of matter in you. The units for mass are kilograms. That's our standard units. Yeah, so mass is just how much. It doesn't change. That's important. So it doesn't change unless you lose some weight, although I don't want to say that word too much. It doesn't change. So if you go from here to the moon, you have the same mass. You're here on Earth. You go to the moon, same mass. Because it just depends on how much stuff makes you up. That's versus weight. Weight is a force, and it's a force exerted by gravity, wherever you are. So it's whatever pull gravity has on you. The units for this are newtons, because it's a force. And this does change, so this changes. It depends on where you are. So if you were going to go from the Earth to the moon, your weight would change. So you'd have a different weight. In fact, if you were just on Earth and you were down at sea level and then you went up on top of a mountain, your weight would change as well. Because gravity, as we move away from whatever object has that gravitational force, G, which is the symbol that we use for the gravitational pull, decreases as we get away from it. And we'll talk more about gravity later or after Christmas. All right. So these are related. Your weight depends upon your mass, but mass doesn't. Mass doesn't depend on weight. So weight depends on mass. It depends on two things. It depends on your mass, and it depends on where you are. And so our weight, we define as the force of gravity being exerted, and we can write it with a big W. That's weight. And it's always equal to your mass times the gravitational pull. And that G depends on where you are. So on Earth, G on Earth is 9.8 meters per second squared. That's the acceleration due to gravity. And so that's how we calculate weight. So when we say weight, we say mg. All right? So just as an example, what is the weight of a 60 kilogram person on Earth and on the moon? So the weight on Earth would be the force of gravity on Earth. So that would just be m times g on Earth. So that would be equal to 60 kilograms times 9.8. And we would get whatever we got there. Now the weight on the moon, that would be the same mass, but now times g of the moon. So it'd be their 60 kilograms, where g on the moon is about 1.62. So you can see there's going to be quite a difference, about an eighth, if we go up to the moon. However, the mass did not change. Mass didn't change. The weight did. Mass doesn't. All right. So now we need to talk a little bit about apparent weight. Oh, let's do one other thing. Let me show you another example, another type of problem that can come up. It's pretty easy math, but what's the mass of a, we'll say, I don't know, 700 Newton person? Okay, so the way that this is written, this should give you a hint. This is a newtons, so that's a force. So we know we're talking about weight here. And we know that weight is equal to mass times g. So if I want to know the mass, I would just divide. So mass would be the weight divided by g. And we assume this is on Earth, so it would just be 700 divided by 9.8. That would be the mass, whatever it is, a little bit less than 70 kilograms. Okay, let's talk about apparent weight. So we could define apparent weight. This is what your weight feels like, apparent weight. And this would be the sum of the supporting forces, the sum of supporting contact forces. Contact forces. All right, so let's think about that. We'll build up to it. So let's just suppose that you're standing on the ground here on Earth, and you have a mass, whatever it is. Okay. So thinking about a force diagram, your center of mass, you're going to have some weight. Now you don't feel the weight. What you actually feel is the normal force pushing you back. It's counteracting your weight. So in this case, my weight is, the normal force is equal to my weight. So the normal force that I feel, the ground pushing me up, is equal to my weight in this case, which is equal to mg. And this isn't always the case, okay? So don't fall for that. Don't always think that the normal is mg. And we'll talk about the normal next. But anyway, the apparent weight is your actual weight. So this is actual. Put a little a. So your actual weight is now your apparent weight. They're the same thing. Okay, so that's kind of boring. What we care about is what happens, like say if you're in an elevator and the elevator is accelerating upward. So we have some acceleration going up. That means that we have a net force. So we have another force here. We have the normal holding us up, counteracting the weight, but now the elevator is also moving with another force. We'll call that the force of the elevator. So there's another force that's pushing us up. And so we want to be able to determine what that is. And so this force here, the force of the elevator, would just be my mass times the acceleration. That's how I could figure out that force. That comes from Newton's second law. This is the acceleration of the elevator. Let's put a little e there. The acceleration of the elevator. Okay, so apparent weight is the sum of the support contact forces. So we need all of the forces. So my weight apparent is going to be all of the forces in contact. So we can see I have the normal force plus this new force, this force of the elevator pushing me up because it's accelerating. And now we can substitute. So my normal force was mg, and then the force of the elevator, that's going to be mass times, that's mass times the acceleration of the elevator. And if I factor out that, what I get is I get mass times g plus the acceleration of the elevator. And that makes sense. That makes sense. So it's my gravity, it's the force of gravity, and then we have this other acceleration. So we're just going to add it on. The ground has to counteract the 9.8, and then, or the ground of the elevator, and then the elevator is actually moving up. So we got to tack on that extra acceleration. So I'd actually feel heavier. I'd feel more force pushing me up, and that makes sense because my acceleration, my g is bigger because I'm adding on the acceleration. How would that work if it was accelerating downward? So think about that. When you're in something and it's falling, you feel lighter. You feel less apparent weight, and you should be able to guess why. So in this case, we're going to have the normal pushing up, and again, it's a level surface, so my normal is going to be equal to mg. It's counteracting my weight. But now I have acceleration downward. So now what I have is I have a force this way. Yeah. All right. So when I do my weight apparent, it's going to be my net force. So what I'm going to get is my normal minus this other force of the elevator. So I'm going to get mg minus m times the acceleration of the elevator. So it's going to be m times g minus the acceleration of the elevator. So what I can do is, depending on the direction of the acceleration, I either add or subtract that acceleration on and multiply by mass, and that gives me my apparent weight. And this leads us to another thing, or another concept. So we can start subtracting. We can start subtracting this. And what that is that's an object that's accelerating down. So that's my acceleration. So what I want to know is what's going to happen when this is equal to 9.8 on Earth. Well, when that's equal, this whole thing goes to 0, because it would be g minus g. And so I would get 0 times my mass. So my weight apparent would be 0. And this is weightlessness. Weightlessness. So you're falling in the air. You're weightless. Now you still have mass and you're on Earth, so there's still g. It's just that you're falling at 9.8, and that's counteracting, or that sums up to be 0 because of this right here. So the only time that you have weightlessness is in free fall. That's the only time that you'll ever be weightless. Because even if you leave Earth and go up in a spaceship or a big fish, you still have weight. It's just very, very small. Gravity goes forever. It's infinite. All right, so that's a weight and mass. Go try a couple practice problems and we'll see how you do.